Hi students, we have learned about series circuit and parallel circuit, but sometimes there are more complex circuits that cannot be broken into mm, either series circuits or parallel circuits. So in those cases, it's important to know and to use the Kirchhoff rules. Kirchhoff rules are used, as I said, to work on circuits, that are pretty complicated, that are complex. And we have then two rules that are the junction rule and the loop rule. And the junction rule is a consequence, of the law of conservation of the charge. And we're going to have the loop rule that is a consequence of the conservation of the energy. The junction rule says, that at any junction, the current entering the junction must be equal to the current leaving it. So, for example, in the circuit that I have here, I have this current I1 that is entering into the junction A here, right? And when the current I1 reach the junction A, find two different paths. So this current will be split no in 50-50, you know what I mean? So, just the half to one branch and the other half to the branch. It depends on the resistance that are involved here and all the other components. So, but basically what happens is that the current I1 is broken, into I2 and I3, so that the current I1 should be equal to the total of I2 and I3, right? Because the current entering into the junction should be equal to the current leaving the junction. So here is just how we see the junction rule. Sorry, in this case. In the other hand, we have in blue the loop rule. Sorry. And the loop rule say that the algebraization of the potential difference around a closed loop must be zero. So for example, I have here one loop that is this one over here, you know, and the components that are just uh, part of this loop are these battery I have here with an electromotive force or an electric potentially. We have all going all around this resistance one. We have this other battery uh, with an electromotive force or mm, electric potential E1, and we have this other resistor, R3. So if I say that I1 is the current passing through this part, and I say that through R1 is passing the current I3, and then I say, of course, that I3 and I2 join at this junction again. So to the left of this junction over here, what we have is again the current I1 that we had over here. I can say that the variation of voltage, the electromotive force of the battery that I have over here, as I am going in this direction, I'm going from negative to positive, so it's positive, uh, minus the drop of voltage to this resistor, because when you pass through a resistor, you go from high voltage to low voltage, from the higher voltage to lower voltage. So you have here, that there is a drop of voltage, so that's why we have a negative sign here. The product of the current I3 times the resistor 1 minus, again, we have a drop of voltage in this battery, right? Because we're going from the positive pole to the negative pole of the battery. So we have minus A1 or minus the electromotive force 1 minus then the drop of voltage uh, across R3, the resistor 3, right? Again, negative, because when you pass through a resistor and you go in the direction of the current, you go from positive to negative. So I have minus I1 times R3 over here. That would be zero because I don't have any other component in this loop. So basically in this loop, I have, this battery, this resistor, this resistor. I can have a second loop that should be here, you know, and I can have a third loop if I need it, that is gonna be all around here without considering, this segment of the circuit. So this part of the circuit just going all around, you know, with this speed loop. So this is how you use the Kirchhoff laws, right? Or the Kirchhoff rule. The problems are pretty complicated, and in the next video, we're going to explain the solution of one example.